Oh, Niranjan.
Hi, Dr. Sajid.
Uh, yeah, I see you. We changed our room, so or we were driven out of that. It's not a choice. No. Did you get the names? I think what you see on your screen. Oh, I should know the names. Dushmanta on the right and Sandarupa on the left. Niranjan and the two more students managing the camera.
Did it turn on? Does it any check? It's on. Yes, it's I think laptop's camera.
No, it's not on. The power, it's not getting the power. Yeah. They moved this table, correct? So now it's actually better. How you can use a bigger part of the whiteboard. Earlier that used to be table with here. So you could use only parts. But it's not bad. Except students, I don't have a backers.
Yeah.
It's a long class. You found a backers. Okay. So it seems like we will be in this room. The other room is occupied by Puneet Kohli from the chemistry department from 10 to 10:50. So it's not that the whole time he's occupying that. And he also says he would prefer it on the third floor. So, or he mentioned to me that he would like to know. I don't know how easy it is. I don't want to do any of this because from what I understand, upper administration really doesn't like this. Any discussion of this leads to a 1 hour of discussion about why this is not a proper event. So, I'm not going to take any initiative. In case Puneet moves, then maybe we can consider moving. That is it. Okay, so there was a confusion about so there was a confusion about midterm one when it is apparently it's September 29. How do you answer that out? It's a Friday. And you want it in class, that's all. By default, it is in class. That means from 9:35 to 10:50. I always tell the students that if they think anything else is better, that means that outside the classroom in the evening, which means you can have extra time. I'm open for that, but you guys all need to think about if you have an open time between yourself before you tell me that. It doesn't mean that the exam will be any different. It will be the same exam. Typically, I think it is sufficient 1.5 hours, and I've also seen that sometimes what I do is more than half of the exam. I make it take home, and you bring it, and in the exam itself, there is only very elementary questions that you do. So usually half an hour is sufficient for the exam. There are few questions that I test on. And it's just a matter of making it. So typically, all this has not come, or recently in the last 2 semesters, it has not been an issue. But still, if you would like to have an outside a different time exam, that has a small advantage that I can use for teaching, which I'm not sure again whether it's appropriate or not, like here. You will be working on an exam in the evening, and in the morning I take an exam, sorry, you could take lecture. How effective it would be. So it's relatively far, so we can keep discussing this, have this in your mind. If you have any strong opinions on that, discuss among yourselves. And with me also open. My only point is open. Okay. Homework 1 is due on Monday, which means I have to cover a lot of stuff. And it's due and in the this doesn't go all the way. Mailroom. Physics. Everyone here knows where is the physics mailroom? Sandra? No. Physics mailroom is across the hall from the physics office. You all have met Shannon. Like wherever Shannon sits, across from that office, across the hall, there is a room that's called the physics mailroom. There is a copier, there is a printer, and there are small boxes for each faculty and for you guys. You guys have a mail room, and you're supposed to check that, because if I have to put something, for example, Sandra, you're my teaching assistant. If I have to pass on something, I may not come to your office. I'll just put it in the mailbox. So it's expected that you guys check it every day. Like, for example, a student can try to communicate with you. So check your mail room. Nathan, you are aware of that? Yeah. Okay. Okay, any other questions? Okay, so hello. Peter. So we have a new student. Yes. Hello. This is math methods, and you must be a new student.
Yes.
Name?
Nahida Islam.
Nahida. Nahida. Okay, nice. Have you met others here? Oh, sorry, one. Okay, so I'm the only one. We also have. Oh, what happened? Oh, yeah, it's I'm having a video on. We also have another faculty from North Dakota. He's joining us, Niranjan, so you will see him also. Camera. As a new student, yeah. Okay. It's Nahida.
Hey, Nahida. Hello.
Hello.
Nice. Okay, so we have 3, 6, 6. Okay, 8 of us. So hopefully, productive. So Nahida, this is math methods, and we'll basically primarily have homework and exams. There is a homework due on Monday. It might seem that you missed something on the first class, but we didn't do anything. We were shuffling between classes. We struggled to settle down. So we hardly did 5 minutes of something, which I'll repeat here. So you didn't miss anything. As far as the logistic goes, talk to your friends and talk to me. So I think that's the summary of whatever. Okay. Here, today, I want to do what is called index notation. It's basically what is often called, let me call it tensor now. I think a better. But I feel it's a wrong, overstating it. Tensor analysis is, I think when you say analysis, it's a little deeper concept. It is, and but we will be doing very rudimentary part of that. What is called the index notation. That is what I want to give to you, because that is used in other subjects a lot, or whenever you're dealing with vectors, or for that matter programming. You must have seen, or you must have, what is an array in a computer program? Are you familiar with this word, array? Is that familiar? Okay, so quiz. Right, connection between array and tensor. Often, it's a popular terminology that tensor analysis is used for in computer programming, whenever you're doing contractions and so on. Nahida, I think you might not know the quiz. Are you familiar with what a quiz in this course means? Probably not. So homework is a guided homework. I type it down and you're expected to go through. That's the usual homework that you're familiar in every department, every course. Quiz is slightly different. I don't type anything. I don't even plan what I want to ask. So like a conversation like this in a class, suddenly a topic concept array, and I don't want to, or I may not even be qualified to say something seriously about the connection between array and the tensor. Instead, what I say is that go and read about it. So that becomes a quiz. It's a very vague quiz. I have not stated it properly, but the idea is that whatever words I write down here or say, you look it up and write a few words on it. I would recommend that don't spend more than 5 minutes for the purpose of the course. If you like the concept, go and read about it. But for the purpose of the course, just 5 minutes, and the grade, it is graded only for participation. If you get it wrong, there is nothing, it is okay. Like sometimes a question can be hard enough that there is no right and wrong. Okay, is that again odds here? Okay, so just to give a few terminologies, we are already familiar with a few concepts like scalar, vector. Vector typically is defined as a quantity with a magnitude and direction, but we want to get more general than that, and we will define it in a more strict way as a user. Like again, we won't go into the basics where we will start from the scratch, but as a user, we mostly sufficient. We will also say, let's say this is a matrix. So notice what is happening. There is one number. Then you think of a discrete quantity along a line. So that's a vector. So there are 3 components. This is how many components does it have? So this is 1. So this will have, let's say the dimensions is 3. There is 3 components. This will be 3 times 3. So you're thinking of a square matrix. And I can think of a next quantity here. So maybe let's say this will be 0 rank tensor. This will be first rank tensor, and the second rank tensor, and next is third rank tensor. This will be 3 times 3 times 3, and so on. So there is no special name for this. Think of it as a cube, for example. So here you have a number, and you say this is 3 quantities, and you say this is 1, 2, 3. That clear? And then you make a cube out of it. I can do this. Hopefully. Is that clear? So you make it, and this can keep going. I cannot draw this anymore, even in on a flat sheet. At least I cannot. I just imagine such a situation. That's the main idea, and we want to use some symbolic prescriptions and rules to manipulate this quantity. So let's go back to vector, and a vector is usually represented by the quantity vector, like a letter A and a vector sign on it. I often see in your work, see in textbooks, you will write. So this is how I will write it. So this is on a board, whiteboard, or a blackboard, or your notebook, right? In your textbook, they will probably make it bold. So this is boldface, so this is how they will write it in textbook. In your homework, textbook plus homework. Now, because you read this in this form, it is very convenient to think that the vector sign is not necessary. And if you in your notebook write just A, that's not a vector. Typically, there's a difference between a vector and a magnitude. This will be usually a magnitude of. So at this stage, when you're writing it, at least when I'm grading it, it's necessary that I should be able to differentiate between the two. So I think it's important that you separate them out. At least there should be no ambiguity between a magnitude of a vector and a vector, etc. So that's the notation. And what do we mean by that? It's you have a arrow with a direction, right? So there is a length associated with the vector, and there is a direction. And if you're in a plane, this direction is very clear. If you draw, if you can look at this, then I don't need anything else. Like, that's complete information. But the challenge comes if you're not allowed to show this diagram. There is no blackboard, there is no reference, and still you want to pass on that information. Imagine you're writing it, right? When you're writing a paper, let's say in the olden days, you didn't have any figures, and you want to pass on this information anyway to someone else. And you will realize that whenever you say walk in a certain direction, it's always with respect to something, and North Pole is what is used typically. You will say that with respect to the north direction, make a 30 degrees and walk 50 miles. That is how, like, if you go to Google Maps, actually in Google Maps, there is a north direction, right? This axis becomes important. There is a reference line. If, again, it's not important if you can use visual notation. We are talking about only if you do not have this diagram and you still want to pass on this information, you would say go 30 degrees with respect to north, or let's say this to the east. So this will be 30 degrees east of north. That's a notation that comes in, and you will say, oh, go for 50 miles. Think of your telling this information on phone, and you don't have any diagrams, that this can get very difficult to talk. Like you're stuck somewhere in the forest and you don't have many reference, and it will be very difficult for you to communicate where you are. Often you use the stars. So that's the idea we want. This is a geometric idea, direction and magnitude. Now we want a quantitative value to this, which can be used for addition and subtraction. So we have a North Pole, so you immediately say we don't want North Pole, is very specific. Let's take any two directions, make it very general. That is E1 and that is E2. Pick any two directions, and typically it is chosen to be orthogonal. It doesn't have to be orthogonal. We'll come back and talk about situations when it is not orthogonal. That's your E1 and E2, and you say we will define this quantity as this is A1 in the, so this is a projection of A, so this is the vector A in the direction of E1, so this is A1, E1 plus A2. So a lot of things came in here. So EI, so this is just a, whenever I put a hat on it, it is understood that it is a unit vector. And the difference between an arrow on top of it and a hat is that it's unit vector. That means its length is 1. I here means that I could be 1 or 2. I'm working in 2 dimensions, so it could be 2, but easily you can generalize it to 2, 3, 4, 5, and so on. Okay, so EIs are called basis vectors. AI, which is a projection, or AI will be projection of vector A along. Again, just a description of what I am using. These definitions itself are the understanding is more important. So there is a vector. In principle, doesn't need any coordinate system at all. It's a geometric quantity. But if I use a coordinate system, there is a lot of simplicity, and then I have A1 and A2. And often it is possible that you can go a lot without changing your coordinate system. You could be working in a certain configuration of a system where you never have to change your coordinate system at all. And in those situations, you stop writing E1 and E2. Only in those situations. It is important that which coordinate system it is. Like, for example, if you choose your North Pole in a certain direction and you're talking to another set of civilization where the North Pole is in a different direction, especially if you use astrology. In those astrology, the main difference is that 3,000 years back, the North Pole was not in the same direction as where we are, or the North Star was. So all the astrological predictions are in reference to another star which doesn't exist, right? So most of it are not even appropriate these days. In that way of speaking, all these coordinate systems are relevant. But as far as you're in the same coordinate system, you might think that it is not necessary to write down E1 and E2 at the sacrifice of some information. It is simply A1 and A2. Right? You can do everything with A1 and A2, and it is implicitly understood that there is an E1 and E2. But then you get even better. You say that A1 and A2, it is understood that it is one is the projection of A along the I, and I've already noticed that when I wrote this, it is in a single variable. I know that it is I is equal to 1, 2. So you go further and say that this is AI, right? Where I can take 1 and 2. So this is called an index. So I here is called an index. Let me just say it's index. Okay. Oh, hard to read, or maybe Abdullah is blocking that. Okay. Any questions until here? Nothing. It's pretty straightforward until now. A vector A is going to be represented by AI, and at the cost of some information being lost, that it is a unit vectors that is not showing up. Okay, so that's good. So I have a vector. So now when I say a vector, so I have AI, and let's say there is another vector that is VI. And let's think of vector operations. What are the vector operations you're familiar with? Vector operations, huh?
Dot and cross product.
Dot and cross product. Okay, you're already ahead, but let's do a simpler thing. Addition and subtraction. Right? Yeah, good. I want to do dot and cross, but let's do something simpler just for warming up. So, and let's say this is Ci. And let's say vector A plus vector B is equal to vector C. What this means is that you will immediately write this is A1 plus A plus B1 and along E1 plus A2 plus E2 along E2 is only 2. That's equal to so C. I think that's C. That's C1. Right, that's what this equation means. A vector equation generally has two algebraic equations. So this means I have A1 plus B1 is equal to C1 and A2 plus B2 is equal to C2. Is that clear? I'm just explicitly writing down that is an A plus B equal to C. That's the vector equation. That's the geometric information. But now I'm working in a coordinate system. So I'm doing algebra. So this is along E1, E2, and that is an E1, E2 on the right side. But we know that whenever there is a vector space along each direction, it has to break up, which is a very useful quantity when you're doing mechanics. What you're saying is that X motion is completely disjoint from the Y motion, and the only coupling is the time involved in that. So that plays a very important role in mechanics. And what we're saying is basically this. But now, see how this notation helps. These two can be combined. So these two can be combined into a single equation when you write AI plus BI is equal to CI. That's index notation for you. Okay. AI plus BI is equal to CI. How do I get the information in detail? I put I equal to 1, I get this. I put I equal to 2, I get the other one. So that's the important piece here, and that's the only if you call it a concept at all, it's not a concept, it's just a notation that we're setting I is equal to 1 and 2. In this way of writing, this is called a free index. Later on, we will call what is a dummy index. This is I is a free index. So I here will be called a free index. In the sense that if there is an I in one of the terms, there must be an I in every term. You cannot add a scalar and a vector, can you? Can you add a scalar and a vector? Quiz. Okay. Can you add a scalar and a vector? Or the question should be, why cannot you add a scalar and a vector? Let's say that you cannot. Why cannot you add a scalar and a vector? Give me a good enough reason that why that's not possible. Okay. So since we cannot add a scalar and a vector, if this is a vector, this also must be a vector. That means that if there are one index here, currently we are working with vectors, that is only one index we have. This also should have one index. If this is I, this also should be I. You cannot have a I plus AJ or BJ, let's say, is equal to CK. That's not okay. Like here, why is that not okay? Indices don't match. Indices do not match. Actually, make this also a quiz. Why is this not okay? Why is this equation not okay? I'm not explicitly able to tell it. So think about, like, the main content is here. Like, this is not that. This equation is this, but this is not that. So try to articulate why this equation is not correct. Is this clear? Okay. So that's your vector equation. So what we have is this. So whenever you have a vector addition, you forget about all these details. The same information is in here. as far as you have this or implicit understanding that there is a coordinate system or a basis vectors are understood. You can talk about subtraction, so that's subtraction part. So then everything else goes through. So put in a minus underneath, and that's all. There's nothing more that is needed for subtraction. But you all told me that when I asked what are the operations, addition and subtraction seems to be trivial in vectors. You told me scalar product and vector product. So that's what we would like to do. And for that purpose, we need to talk about something more than a vector. We need to go to a second rank tensor. So what's the easiest second rank tensor you can think of? If you think of a matrix, what's the simplest matrix you can think of? A diagonal matrix, 1, right? 1 and a 1, so that's the simplest matrix. So let's define something called Kronecker. This will be called a delta. Since delta. As a Greek letter. Delta symbol. So what this means is now, first of all, it's a tensor of second rank. So this will have delta I. Now there are two indices. This is the first time I have introduced two indices. Like we had a I, one index. Now I can go from 1 to 2. So what this means is that I can go from 1 to 2. J can go from 1 to 2. So there are how many combinations? Like 2 times 2, 4. Right? So there are 4 combinations. So, and then I set a rule. I set a rule that if I is equal to J, or I should say the other way, right? So it is equal to 1 if I is equal to J, and if it is equal to 0 if I is not equal to J. And that takes care of all the possibilities. Let's see what this is. Notice that the vector A here, here. Vector A is not really equal to AI, because that's not okay, because on the left there is a vector sign, on the right sign there are only components. You need these basis vectors for it to be equal. So this is not really equal to a second rank tensor. These are the components of a second rank tensor. This is not exactly a vector. These are the components of a vector in the basis of EI. So since we are assuming that EI is always the basis, this is what it means. So we want to understand where this stands, correct? So the vector itself, so first of all, let me write this down. So this is delta 1, 1 is equal to 1 because I is equal to J, right? I equal to J is 1. Delta 1, 2 is equal to 0 because 1 is not equal to 2. And delta 2, 1 is equal to 0. And delta 2, 2, that's the only possibilities, that's equal to 1. So that's your, and you can see the matrix structure there. There are 4 pieces that it's a unit matrix. But now I would like to write it in this form. This was a pure vector. There were 2 components. What is this in the complete index? In the basis vector notation. So let's have the Kronecker delta as 1. Now it is a it has 2 indices. So I'll put in 2 vectors on it. So it's a very rudimentary way of writing it. It will be hard to generalize this. You can always generalize this. So for example, that's a vector. That's a second rank tensor. You can say third rank tensor would be like this and like this. Like you can build your own notation, right? A fourth rank tensor would be, but this is not what we will be doing. In principle, you can. Like, and you will have to say this is the first one, second one, and so on. You'll have to label them. All that is possible, but we will restrict ourselves to going on here. Then we go further. Index notations is what we will use. But okay, so with that in mind, this is now not a vector. This is, in a sense, in very simplistic sense, it's a double vector, and it is often called a dyadic. So it's a unit dyadic, and this is equal to, now there is 1 times E1, E1. Okay. Notice, usually when you write two vectors, you either put a dot product or a cross product. Right? You never write two vectors, probably you never write two vectors without any operation in between. But I've written two vectors without any operation. And that is how it is. If that's a new entity, if you want. It's not a vector. It is not a scalar. It is a double vector. So that's why there are two vectors sitting in there. That is, they are not operated. It is very often, this is like an outer product. In many of the textbooks, you will write this as an outer product, not a cross product. This is an outer product. But I won't use that symbol. So here it is just two vectors sitting with each other. And if you're taking a dot product from the left, it will hit on this vector. If you're taking the dot product from the right, it will hit the right one. In your homework, that is a vector that I give you. Like I give you two vectors, construct a dyadic out of it. And then I ask you what happens if you take a dot product from the left? What happens if you take a dot product from the right? What happens? The cross product from the left and dot product from the right. So various things you can do. The last part of your homework, which seems very long, it is actually straightforward if you know what we're doing. Okay, it is just like this. What is one dotted with? So for example, let's say, suppose it is just this one dotted with E2 would be equal to E1 dotted with E2. That's equal to E1 times E1 dotted with E2. And what is E1 dotted with E2? E1? 0, because they're perpendicular, they're orthogonal, so at 0, that's 0. These are the things that is asked in the second page of your homework. It looks very long. It's lengthy, but just to make you guys work a little, just to realize what this notation is. Or what I noticed is that most of you guys struggle with what is implicitly understood as a vector. That's all. So that's why it is a long time. But we are having particular in mind. I'm actually talking about a unit dyadic. So this will be. This is what it means. So there will be 4 components. The order is important, but it doesn't matter where I write it. Now it is an addition, so that I can write it wherever I want, but I have written it in the same order as a matrix. So this is 0, E2, E1, plus 1 times E2, E2. Same information as this, but I have written it in a certain form, exactly like here. A vector A can be written in this form or as AI. Right? So this one, clearly, there is a lot of simplicity if I don't write my basis vectors, and I simply say this is the same as delta ij, which is 1, 0, 0, 1. Again, this is an understanding that these are the 4 components of it. Notice these are the 4 components, right? 1, 0, 0, 1 are the 4 components of the dyadic, which I'm talking about, the simplest dyadic I have built. In general, so this is a unit dyadic, maybe. This is a unit dyadic, very useful. And we don't have it, yeah, we have it. Okay. A more general dyadic, for example, let's say M would be, now I have to give it a name, M11, E1, E1 plus M 1, 2, E1, E2 plus M21, E2, E1 plus M22, E2, E2. And you immediately say, I don't want to write all these bases. I'll simply write Mij. Okay. So this is a second rank tensor. These are the components of a second rank tensor in the basis of EI. Clearly, you could think of a third rank tensor in the way we said. I can have 2 vectors and a third one, and this will be Mij. Even though I use the same letter, these two cannot be the same. One is a vector, one is a second rank tensor, one is a third rank tensor, they cannot be the same. So they're different quantities. Okay, so that's the simple understanding, and we have a specific second rank tensor, which is the Kronecker delta. But I said I'm doing all this because I want to introduce. Oh, I can keep going that way, right? Oh, we have more freedom. Okay. So we want to do cross product. So let's do some manipulation in here. So let's say delta Ij and yeah, so maybe before that. Is it visible up there? Across the region? Can you read?
Yes. Yep.
Okay. Yeah, so this is now index, let's say summation notation now. It's often said Einstein's summation notation, but it's just a notation. You don't have to give a name to it. So let's say you have a vector A, and of course I can multiply it with a 1. Now what does that mean? Like notice this is a matrix. That's a vector or a tensor and a vector. I've done a lot of things there, a lot of few things in here. But in the way we have done this, maybe it is clear. So how we will think of this is that is a vector A, I in the index, right? And I'm now multiplying a 1 in there. So how I will say this is that this is the same as let's say A1 AI times how was it? Give me a second, sorry. So let's write this as summation of J is equal to 1 to 2 times Aj times delta of Ji. So what does that mean? Remember the summation. What this means is that I have to put J equal to 1, J equal to 2 on it. So let's expand this out. Is this really the same thing? So is this really true? So let me say for J is equal to 1, right? So this is A1 delta 1I plus A2 delta 2I. So I'm claiming, so let's say this is not obvious. Let me say this is a question mark. So I'm going to show you that this is actually the same as this. So I'm claiming that AI is nothing but multiplied by Aj and then a unit vector. And notice what is happening here. Is this really true? let's check it, right? So there are supposedly two equations when I is equal to 1. A1 is equal to A1 delta 1 plus A2 delta 2 delta, no, 2 delta 2 1, thank you, sorry. So that's 0, that is 1, and that's indeed 1. Right, so that's checks. So that's correct. So this is A1 plus 0. Let's do I equal to 2. And this is A2 delta 2 1 plus H. No. Again, H2, did I do this one? H1. I is equal to 2. Oh, yeah, this is 1 delta 1 2 plus A 2 delta 2 2. This is 0 plus A 2, that also works. And you can check this even if this is n dimensional, it will always check. So it seems like this is a good way to write AI, right? A complicated way, but you will see that it has meaning when you're writing dot product. So what I've done is AI is equal to j equal to 1 to aj delta ji. That seems to be a lot of baggage to carry. So the simple two quantities, two components, I will represent this in terms of a correlation of quantities. Here is now the notation comes, the summation notation. This is sum. So I'm going to get lazy and not write the sum anymore. So this is just going to be aj delta ji. These two are going to be the same. So I stop writing the sum. One would think that that's a bad idea because you're like there was a symbol that was meant to do something, you're taking away that language, right? But that's where the notation comes. How do you know that you have a sum it? Here there is clear instruction that sum on j. Here there is no instruction, so it's implicit here. So this is called the summation notation. So the idea is that j is sum because it repeats. So the notation is, that repeated index in the same multiplication term, if an index repeats, it has to be summed. Has to be summed or is summed. Then this should that is summed. That's the notation. Okay. Repeated index is summed, and this repeated index is called a dummy index. Any index that repeats is called a dummy index. Any index that does not repeat is called a free index. Right, there are two indices we will talk about, free index and a dummy index. This is a dummy index. So that's a notation. Now how do we use it? So let's begin. So the classic example. So let's say example. So we ask, what is delta I? Equal. Yeah, so the understanding is somewhere means that we working in 2 dimensions. Yeah, in 2 dimensions, so n dimensions, let's say. N, right? So it's repeated, yeah, good, right? So this is repeated, so the understanding is that this is sum of I is equal to 1 to, let's say, n dimensions, delta I I. But delta I is always one, right? So it is 1 plus n times, so it's n. And that is nothing but the trace of the unit matrix. If you think of a matrix, it is a trace of a unit matrix. So this is also equal to trace of 1. So just based on that simple notation, we are able to do a few things. And yeah, so now let's say dot product, right? Scalar product, dot product, A dotted with B is equal to, when you're working on a scalar product in terms of components, what is this? A1, B1 plus A2, B2. Is that clear? So when you're taking a dot product, it is the components that multiply. That's clear? So that's nothing but summation of I going from 1 to 2, AI, BI. Summation index notation, that's nothing but AI, BI. So dot product is nothing but in components simply AI, BI. Is I here a free index or a dummy index? It's repeated. So dummy, right? So whenever it's repeated, it's a dummy index. Right? So that's the understand. So this is a dummy index. When it was showing up here, right, there was this equation. Here it's a free index. It's like take one term out of it and it's not repeating, so it's a free index. Here I is a free index, here it is a dummy index. Is this quantity a scalar or a vector? A dot product is a scalar, so there are no free indexes. So whenever there are no free indexes, that means it is a scalar. Okay, that's your dot product for you. Now we next want to build is a cross product. So for that, we have to go to the next. So we need a third rank tensor. So this is called Levy spelling. Levi's. Think so. Check the spelling. Like we had the Kronecker delta symbol, Levi-Civita symbol. Now this is not a second rank tensor, it's a third rank tensor. So on I, J, K. How many dummy indices in here? In this expression, how many dummy indices? None, right? How many free indices? Right, 3, 1, 2, 3, 5. Now the understanding would be, so remember I, J, K, and now let's say we are in 3 dimensions. N is equal to 3. For concreteness, let's say N is equal to 3. I say epsilon, this is equal to 1 if plus 1. If I is equal to 1, J is equal to 2, and K is equal to 3, and cyclic combinations. What does that mean? Let's have I here, J here, K here, and let's have this is a circle, right? So that's a cycle. If they come in that order, that's a cyclic combination of I. So epsilon 1, 2, 3 is equal to plus 1. I is equal to 1, j is equal to 2, and k is equal to 3. And any combination of that, so this is 1, 2, 3. I can have 2, 3, 1. So 2, 3, 1, that's equal to plus 1. 3, 1, 2 is equal to plus 1. Anything that is in the cycle. What is not in a cycle? So for example, 3, 2, 1. If I go the opposite direction, then it's 3, 2, 1. So that's not a cycle. Then it is a minus 1. Right? And it is a minus 1 if I is equal to 1, j is equal to, so I'm going the opposite way, right? And k is equal to 2. And cyclic combination. And it is 0 otherwise. This is a third rank tensor. How many components will it have? 9?
27.
27, correct? Third rank tensor 3. I can take 3 values. J can take 3 values. K can take 3 values. Right? So there are 27 components in it. Like we had delta ij, there are 1, 2, 3, 4 in 2 dimensions. There are 4 components. There are 27 components. So here is a quiz for you, an important quiz. Do this, very important. Write down all the 27 components. Is that clear? The assignment? Write down all the 27 components of the Levi-Civita symbol. Okay. I gave you a few quizzes here, but this is the most important one out of them. Okay. So that's Levi-Civita symbol, and now let's do cross product. This is cross, right? Cross product is you would say A cross B. Notation is fairly standard. I don't think almost every textbook I see use it, unless you go 100 years back. Okay, then they have not established that notation. Yet, so it is A cross B is equal to C. You would like to write this in index notation, that's the goal. And the claim is, the following is the index notation. Right side is clear, right? That's a vector, that's Ci. There's only one index because it's a work vector. And I can write any index I want. I pick I, usually the I, J, K, but I can pick any index I want to, let's I write I. Now, on the left-hand side, what is it? So the claim is that the left-hand side is epsilon I, J, K, and then AJ, BK. So now we gotta verify, is this really true? I mean, we should verify this. First of all, there are how many free indices on the left? How many free indices? Again, how many say 1? How many say there's 1 free index? Many of them. How many say 2 free index? How many say 3 free index? Okay. How many? Let's try the dummy index. There are how many dummy index? Is J a dummy index? Right? It's repeated. Yeah, there are 2 of them, so it's dummy. And whenever there is, if an index is showing up 3 times, you made a mistake. It cannot come. Okay, so there's some error you have done it. So either an index will show up once or it will show up twice. If it is showing up 3 times, it's something you have not taken care of. most probably you have used the symbol more than once. Okay, so it'll never come 3 times. So it will either come once or twice. J is showing up twice, so it's dummy. K is showing up twice, it's dummy. I is showing up once, it's free. Another way of checking is that on the right side, there is only one free in there. The left side has to have only one free in there. Because you can only add vectors or add and subtract vectors, so dimensions has to match. So if that's a one index, this should also be one index. Okay. With that, let's go back. What is A cross B, by the way? So it is supposed to be in E, so it will be A2 B3 minus A3 B2. Notice that, so this is E1, right? Plus E2 times A3 B1. Is this correct? Am I having the correct sign? Anyone thinks it's wrong? B3 is A1 B2 minus A2 B1. We sometimes use the determinant structure to remember this, but remember there is a -1, but I've taken care of this the other way. But notice, in this way of writing, there is this nice symmetry that's showing up. The first component will have 2 and 3. 1, 2, 3. Cyclic. 2, 3, 1. The cyclic property is there. 3, 1, 2. Cyclic. Right. So this way of writing has that cyclic property inbuilt in that. And that's an intrinsic property of the Levi-Civita symbol also itself. Geometrically, it has more insight in it. So we want to verify this, right? So we should be able to do this in here. So how can we do this? So let's set I equal to 1. Right. So then the left hand side is, or right hand side will be C1. That's equal to epsilon 1 JK AJ DK. Right. This is a summation in J and summation in K. So I will do that. So this is epsilon 1. Now I'm summing over J alone. So that's 1 K 1 DK plus epsilon 1 2K A2 DK plus epsilon 1 3K A3 DK. Is that clear how I expanded? There is a summation in J because it's dummy. There is a summation in K also. I can do any sum I want first. I'm just doing the summation on J first, keeping the K as such. Notice epsilon 1 1. So what will be epsilon 1 1 3? Right. Look into this and tell me what is epsilon 1 1 3 out of this. 0, right? Because it is neither 1 2 3. So this is all you have to be different, right? If it is, or another way to remember is that if the index repeats, it is 0 in epsilon ijk alone in Levi-Civita symbol. So this is 0. So that's gone. That's it. Okay. That's only one that goes away. I expected more to go. Okay. Let's expand this again. That is epsilon 1 2 K again expands. So it will be 1 A2 B1 plus epsilon 1 2 2 A2 B2 plus epsilon 1 2 3 A2 B3. And then do this expansion. That's 1 3 1 3 B1 plus epsilon 1 B2 A3 B2 plus epsilon 1 B3 A3 B3. Again, all the repeated ones you can get rid of. One repeats, that's 0. 2 repeats, that's 0. That's 0, that's 0. This survives. This goes to 0. This survives, that goes to 0. And there's only 2 things that survives, and that is epsilon 1, 2, 3, A2, B3 plus epsilon 1, 3, 2, A3, B2. 1, 2, 3 is cyclic. 1, it's a plus 1, that's plus A2, B3. 1, 3, 2 is going in the anti-cyclic form, so it's minus A3, B2. And that's indeed correct. C1 is correct. Again, quiz, there's a lot of quizzes today. Right? Check this for C2 and C3. Okay, so that's typically there is not so much of work in quiz. This is unusual, but seems like there was a lot of work in the quizzes. Any questions until now? If you've done cross and dot, you can mix this up, right? You compound it, that's common. And let's mix up a simple one. And if I get time, I'll do the other one, right? So let's say that is A dotted with B crossed with C. And in this case, it's good to put parentheses, but again, it's sort of understood because if you do this first, then the second operation doesn't make sense. So let's have that clear that the parenthesis is on B and C. Okay. You want to do this using index. First, do the dot product. That's AI, and then B crossed with C. It's the ith component of B cross C, right? That's how you would do it. And then you come back and do the cross product, and you would say this is epsilon I J K Bj Ck. Suddenly, and once you are in components, you can write it anywhere you want. AI, which is all, those are the things you learn from doing homework, that you can move things around and so on. So this compound operation is this. Let's do instead A cross B dotted with C. These two are not the same. Are they the same? Could they be the same? Maybe that's a confusion you have. In vector algebra, usually you're not very sure immediately as to what's the operation. You want to suddenly check that these two are not the same or not. Expand this again. So this is A cross B. Vector notation, that's C I. That's equal to epsilon I J K A J B K B I. So, and we get these two. Are these two the same? The advanced question level, but you can answer like advanced with the sense that it'll be very powerful to deduce them. Are they the same? What about the left hand side? Are they the same? Using vector ideas, not index ideas are probably new.
Looks same. We can switch dot and cross.
Yeah, you can switch dot and cross, right? In vector algebra, you learn or you realize that you can actually switch. So these two must be the same. These should be the same. Now that the index, we are learning this, so it's okay if you make the same. This doesn't look the same, right? So there is AI This is a J. It seems like it is not the same, but they are the same. So how do we see this? Notice. Let's begin. Let me begin by asking. How many free indices here?
No.
There are no free indices. I is repeated, J is repeated, K is repeated. This is a scalar, there should be no free indices. So everything is repeated, so there is no free indices. Now, when there is a, let's say, M dotted with N, often you say this is Mi and I, right? What if I write Mj and J? Is there a difference between these two? No, because it's a summation, right? I will say I going from 1 to 2, J going from 1 to 2. These two are the same. So whenever it's a dummy index, it doesn't matter which letter I use. So this doesn't matter what I use. So I'm going to say, since I want to match it with this, A should be. So let me call this, wherever there is a J, I'm going I prime. Since I've used I here already, I don't want to use I itself, so I'm doing I prime. Wherever there is A, so this is I prime. No, J is I prime. I prime. K is K I want J, right? So this is J prime. So this is J prime. And C is I want this K, K prime, and that is here. Okay, so I just wrote primes because I didn't want to confuse, because I've used up I itself. Now that I've written it, I can use it as I want. So now I replace K I J. I can use any letter I want. Is that okay? So now I can compare that these three are exactly the same. By all this manipulation, I've got the indices of these three the same, but this doesn't seem to be the same at least. So now I have to use the property of Levi-Civita symbol. I'm doing the cycle here, K, I, J, right? So I, J, K. So I can notice I, J, K. If I'm going in this direction, I, J, K is the same as K, I, J. So if I go cycle, it remains the same. So this is the same as I, J, K, A, I, B, J, K. So indeed, that is the same, but here you have to use little. But once you know the tricks, then notice you have to do only 3 steps, or it's less than 3 steps. If you had to verify this on using the components, you might do a little bit more work and a little bit of tedious work. And especially if there are 3 dot or cross products, it becomes a little ugly. And here in this is much easier. I've noticed that whenever I give this vector algebra problem, it is common for you guys to do it the explicit way. Don't use the index notation. My recommendation is, the idea is to practice index notation. So use the index notation. Try not to use the algebra itself. You don't use a vector index. Okay, that's all. Thank you. Niranjan, could you read what I have direct form?
When you started the second half of the whiteboard, it was a little blurry. Other than that, everything was perfect.
Yeah, we can zoom this more, so we'll make it 4 pieces of the board. Like instead of 3, we can zoom in more actually. Yeah, we can do that. Yeah, yeah. Just let us know so that whenever I ask, so it's very easy on the camera to do it.
Okay.
It's just we have to change it more often. You will have a lesser view, overview kind of. Okay. But anyway, this is mostly familiar to you, so the
Yeah.
big warming up in that. Okay, thanks.
Thank you, Dr. Sajas. Then, yeah.
Yeah, talk to you later. Yeah.
Bye.
Bye. You guys have it. Yes.
Get 2 more sheets.
Oh, homework sheet. Okay, so I don't have it. Oh, maybe I have my copy. You can have my copy. Okay, so I. Usually the idea is that there is a web page for the course. And for that, contact Sandra. How you get to the web page? Ask one of your friends. There you can download it. Or search my name, you will reach there on Google if you search my name. You will reach. But don't spend more than 1 minute on it. You just ask Sandra and he will. Or tell her instead of yeah, it's Sandra job. Sure. Okay. Have you settled?
Yeah.
Nahida, right?